emission and absorption of radiation by a system, so an atom with one electron, let's say. So now we're going to talk about not stimulated, not like an external force or driver or something is applied. It'll just happen spontaneously. Okay? So spontaneous emission of radiation. So the radiation just comes out of its own accord. It's not pushed, in a sense. It's not stimulated by some external source or driver or some. Okay. Now, the stimulated emission, when photons fly out, let's say, or absorption of a photon, so they, as we've been talking about the quantum mechanics of that, stimulated emission and stimulated absorption, that there are classical analogues, something equivalent occurs classically as well. For example, say you've got a simple harmonic oscillator, SHO, and you have an external, it's driven, you apply a force to it in the form of a sinusoidal, just sine or cosine electromagnetic field. So we're talking, I don't know, maybe you've got an oscillating charge, simple charge, so oscillating SHO, simple harmonic oscillator, and you apply an electromagnetic field to that, classically, in terms of classical analysis. Well, that oscillator, that oscillating charge, let's say, it can gain or lose energy, and it depends on the relative phase angles, like the phase of its own oscillation, of this, and the phase of the applied radiation. So, remember the phase, it's the angle, where are you in the cycle, one cycle, like phase 0, like say, it corresponds to, say, like here in the cycle, that would be phase pi over 2, pi, 3 pi over 2, 4 pi, 2 pi, 0. Right? So depending on the relative phase of your stimulating electromagnetic field and the phase of the oscillator itself, the energy of this oscillator you're going to actually gain or lose depending on your two phase angles. Okay, so in other words, there are classical analogues to what we've been talking about. Now we're still, for this last part of this session, continuing to talk in classical, but some phenomenon occurs in classical physics that motivates you to think, well, is something equivalent possible in quantum mechanics? Now, so what is this phenomenon? Well, a classical system can emit energy spontaneously, right? So without some external driver, without some external stimulus, or, right? So it can radiate energy. For example, say you have an oscillating electrical charge, like this, as in like a radio antenna, let's say. Now we know, if you've done some electromagnetic theory undergrad, an oscillating charge will radiate energy, and it just does that spontaneously. It's not sort of driven or forced. It just happens because it's radiating, oscillating. Okay, and you don't need a driving force. It'll just do it spontaneously. Now, took a little bit of theory now, a bit of numbers and formula from classical theory, electromagnetic theory, and we can then use that as a kind of guide, motivator, a bit along the style of correspondence principle. I've done that quite a few times in these lectures, using the corresponding formula from classical mechanics. So there's a formula in classical electromagnetic or electrodynamic theory, we're talking motion here, giving the power, in other words the energy emitted per second, right, the power emitted in all directions, how much power is there, how much energy is radiated per second by an oscillating particle. Okay, and this power formula, this may be familiar to you if you've done electromagnetic or electrodynamic theory. It's called the Lamour, L-A-R-M-O-R, Lamour formula, and it gives you the power, remember, energy radiated per second, and it's this. So the square of the charge on the electron, the acceleration, that's just r double dot, that's two dots, right? D squared by dt squared, second derivative with respect to time of the position, so r double dot squared, so the acceleration squared divided by 6 pi to c cubed, c the speed of light. Okay. Now, so that's the Lamour formula, and we're talking classical mechanics, right, for the moment. This is just a lead-in to motivate us to think of something equivalent in quantum mechanics. Okay, now let's take an oscillating charge. So we can calculate the power irradiated by this oscillating charge, and let's just say R is some fixed amplitude cos omega t. So it's just doing this, right, at a angular frequency omega. And if we average this power over one cycle, just average it, the average power, in other words, the energy emitted per unit time averaged over the cycle, you'll get, let's see, I'm reading from the top of the next session. Well, I think I'll just wait to the next session. Okay, so you can find the average power, average over one cycle from this, and that formula, that average power, we will use as the guide to find the equivalent power formula for quantum mechanics. So,